Hi and welcome to video 12, unit 4, topic 1, and this is the math method second derivative topic, and we're looking at optimization. In particular, in this case, we're looking at shortest path problems, but this time we're going to do one that involves costs rather than speeds, but you'll see how it's the same principle. So here's example 12. Alton Downs is 12 kilometres north of Rockhampton and Ridgelands is 5 kilometres west of Alton Downs. The road is to be repaired and repairs cost $9,600 per kilometre, $96,000 per kilometre, my apologies. The cost of laying new roads is $120,000 per kilometre. It's been decided to repair the old road from Rockhampton to as far as P and then to build a new road from P to Ridgelands. Find the length of the new road such that the cost of the whole project is a minimum. We're trying to minimise cost, minimise time. There's a very common element to this. So we've got Rockhampton here, we've got Ridgelands there. We're going to build a new road from Rockhampton to P. So I'll call this point 1 to P, and this costs $96,000 per kilometre. And then we're going to build, so not new road, that's repairing existing road. Then we're building new road up to the end, which is point 2 with P in the middle, and this is going to cost $120,000 per kilometre. So there's costs associated. What we're trying to do is minimise the cost. So we want the total cost, and the total cost will be equal to cost 1, which is the orange cost, plus cost 2, which is the green cost. And how do we calculate cost 1 and cost 2? Well, if we know the distances, so let's say we have distance 2 and we have distance 1 and they're in kilometres, then the total cost will be equal to the price of cost 1, 96000, times by the distance, plus the price of cost 2, 120000, times by the second distance. But let's introduce our more common algebraic representation now in the diagram, and that is that we do the same thing we talked about before. Pop an X in the triangle section of the diagram there. It will help us out. So that's going to be X, which I hope you realise makes this 12 minus X. And I'm also going to call this Y. Now I will need this. The relationship between X and Y is that X squared plus 5 squared is equal to Y squared, which is X squared plus 25 is equal to Y squared. And I'll be using that. So let's go back down to my equation, and I've got distance 1, it's 96,000 times by 12 minus X, plus distance 2, 120,000 times by Y, or distance 2, which is Y, and in this case Y is 25 plus X squared, but to the power of a half. So Y, I'll go back to the diagram, Y is the square root of X squared plus 25, and D1 is 12 minus X. So this is now in terms of X. I've cut out some of that initial working, but that's okay to do that in a more complex question in particular, as long as I'm careful about what I do. So I'm going to expand this. And 96,000 times 12 is 1152000 minus 96,000 X plus 120,000 times by 25. Oh, actually I can't do that, so I've got to leave it as just 120,000 times 25 plus X squared to the power of a half. And now I'm going to calculate dC dx, and that 1,152,000 will cancel out, but I do end up with negative 96,000 plus 120,000 times by a half, 25 plus X squared to the power of negative a half times by 2X. Now the 2 and a half cancel out again. You'll see this is sort of happening commonly, and I end up with negative 96,000 plus 120,000 X over the square root of 25 plus X squared, and I'm going to let dC dx equals 0, which means, and I'll write it the other way around, negative 96,000 plus 120,000 x over the square root of 25 plus x squared is equal to 0, which means that 120,000 x over the square root of 25 plus x squared is equal to 96,000. And now I'm going to divide, I'm going to do some cancelling out here. Divide by 1,000 gets rid of those zeros and those zeros. That makes it nice. And would you believe as well that 96 divides by 12? So if I divide that by 12, I get 8. And if I divide that by 12, I get 10. So this makes life a bit easier. I'm also going to multiply to bring this up on this side. And so it gives me 10x is equal to 8 times the square root of 25 plus x squared. Now you notice here I wasn't scared about not fully simplifying. The 10 and the 8 can still cancel out, which is nice. So I might just do that as well. That becomes 5 and that becomes 4. And then I'm going to square both sides, which gives me 25x squared is equal to 16 times by 25 plus x squared. So 25x squared is equal to 16 times 25 is 400 plus 16x squared. And then I subtract that, I get 9x squared equals 400. X squared equals 400 over 9, and x is equal to 20 over 3 when I take the square root. Obviously it could be positive as well. If we go back to the diagram now, it doesn't really make sense for x to be positive, to be negative. So we're going to take the positive answer of 20 over 3. Okay, so now we've got our x value. We've been asked to minimize the cost. So I would obviously go ahead now and do step 5 of our plan, which I keep on referring to, but again this time and commonly with these questions, there's my first derivative. Desperately do not want to take a second derivative because that's already complex enough. So instead I'm going to do a gradient table. 20 root 3 has a gradient of 0, and I'm going to test a point either side. So this is my x value and this is my c dash value, the gradient of the costs. 20 over 3 is 6.6666. So I'll try 6 and I'll try 7, and I'll find that that's got a negative gradient. This has got a positive gradient, negative 0, positive, and therefore it's a minimum cost. Okay, now the question is asked us to find the length of the new road such that the cost of the whole project is a minimum. And the new road is our y value. So we're trying to find the length of the new road, which is y. So let's go back and find our y given our x value here. So if we had have actually read the question initially and interpreted a little bit better, I could have actually done this for y, which might have worked out a little bit quicker, but it's not major because I know that y squared is equal to x squared plus 25. So therefore I get y squared equals x squared plus 25. And so that's equal to 20 over 3 squared plus 25. And 20 over 3 squared is 400 over 9. 25 is 225 over 9. That's equal to 625 over 9. Therefore y is equal to the square root of 625 over 9. Y will have two values as well because y could be negative or positive, but we ignore the negative. And so this is equal to the square root of 625 is 25 over 3, or 8.33 kilometers. So there we have it, our final question 12 solution. I'll just zoom out so you can see the whole thing in one page. It's a pretty big question again, but these ones usually are, so just be aware of that. But we've done all the processes there, we've interpreted the diagram, built an understanding of what we're trying to minimize, solved using simultaneous equations, and then used calculus to minimize that, and check the nature of the stationary point in the process, making sure of course that we've actually answered the question at the end. All the best.